This certainly should be fascinating. This certainly should be beautiful. This certainly should touch our hearts because we want to know the reality. We want to talk about the reality. So I'll start here. I would start here with an argument. What if the most powerful computer we ever imagined does not think in ones and zeros, but it thinks in possibilities? What if the future of computation we have is not about the speed, how fast the things are going on, but about awareness, the awareness of choice? I am Arfat Firdaus, and today we will explore the quantum computers, not just as machines, but as I mean, but as mirrors of how the reality itself functions. And because when computation becomes quantum, when it comes to the level of quantum, you have quantum consciousness and spirituality quietly begin to overlap with each other. Now, from classical certainty to quantum possibility, let's explore this reality. A classical computer is honest and it's rigid. A bit is either a zero or one. We may call it high or low. We may call it yes or no. And between these two states, there's nothing. Nothing in between these two states. Your phone, your laptop, even the most powerful supercomputers that you have, they all live inside this strict certainty. The certainty of 0 and 1. Yes, no. Right, wrong. But nature does not behave this way. At its deepest level, when you look at the nature at its deepest level, the reality hesitates. It explores. And what you have, quantum computers. These computers are built to respect the hesitation. And what's here? Here is the birth of the qubit, the quantum bit. In quantum computers, we do not use those bits, zeros and ones. We use qubits, quantum bits. A qubit is not just 0 and 1. It basically exists in the form of a superposition. This is not a confusion. This is superposition. Both the states, 0 and 1, coexisting. They're not coexisting metaphorically, but they are coexisting mathematically. And suddenly, computation stops being linear as zeros and ones. So, think about human minds, let's take an example. Before a decision, you are not convinced and you are not rejected. You are open. Possibilities exist. That openness is not the weakness. It's creative power. A qubit behaves exactly like that. A quantum bit, it behaves exactly like that. Before measurement, it doesn't commit. Why? Why quantum computers are exponentially powerful? Why they are? Why they have this tendency, this capability? Because one qubit can represent two states at a time. That means two qubits will represent four states. And if I talk about the three qubits, they will represent eight states, eight actions at the same point of time. So in general, if I generalize it to 300 qubits, if I think of a 300 qubit quantum computer, it probably represents more states than atoms that we have, the number of atoms in the observable universe. This is not the faster computation. This is parallel reality. This is parallel processing. Things are happening in entanglement. There's parallelism. And we have this entanglement. When separation is simply an illusion, you're not separated. Now comes the strangest ingredient, as I said. And this ingredient is the entanglement. So you have two qubits, and these two qubits can become so deeply correlated with each other that measuring one instantly defines the other. And the distances between these qubits become irrelevant, whether finite or infinite. In physics, this is something that's experimentally verified, and people have taken Nobel Prizes for this experimental verification. In philosophy, this is something revolutionary. This is revolution. And in spirituality, this is maybe the ancient wisdom that separation is not something fundamental. You cannot separate out the things. And to go with this talk, let's think of consciousness and entanglement. Your thoughts are unified. Vision, you have memory, your emotions, you have an identity. They all arrive together and they produce this unity. This unity basically resembles the entanglement that we write down mathematically in quantum mechanics, as was written by John Bell, not metaphorically, structurally. We have conscious experience. And this conscious experience is not assembled, it is co-emergent. Taking on this quantum computer to something what we call as quantum gates, they are transforming meanings. They are not just states. If we think about the classical logic gate, as science students, they are irreversible. We have the gates. We have AND gate, OR gate, NOT gate. Quantum gates are reversible. You can go back in your states in abstract space. For example, we have a quantum gate, what's known as Hadamard gate, very popular gate in quantum computing. And this great gate creates balance. It takes certainty and turns it into the openness. This is not just physics. This is a principle. This is the principle of transformation. And without destruction, there is tremendous transformation. And then comes the measurement, the moment of choice. Here is the crucial moment. Here is the crucial part. A quantum computer, which works on these quantum mechanical quantum bits, does not give answers until you make an act of measurement on it. Measurement collapses all of these possibilities. You have infinite possibilities that are there, but once you measure it, you come up with just one reality. So before observation, there are many realities, there are many truths. But once you make a measurement, once you observe your experiment, you come up, boom, with just one reality. This raises a profound question. What's that question? Is the observer part of the computation? What's that? Physics answers quietly, yes, maybe. Consciousness as a final interface, as a final argument. And thinking about this quantum computer does not decide, it explores. It presents the probabilities, infinite probabilities. Meaning enters only when conscious observer is looking for it. And the conscious observer reads the result. In this sense, I can say that consciousness completes the algorithm. Without awareness, there's no outcome. Error, noise, and frugality. These are the parts of destroying the quantum mechanical states in a quantum computer. But here is a lesson. Quantum systems are fragile. Noise, a small noise, destroys the coherence. And this is why quantum computers require isolation, especially those quantum computers which are built using Josephson junctions. You need cooling. You need very, very low temperatures for coherence, and you need precision. So this frugality teaches something important, and maybe it teaches the truth at the deepest level. And what it tells us, that the truth at the deepest level is very delicate. It cannot survive. It cannot survive the violence. It requires the stillness. A spiritual reflection coming from physics. And many spiritual traditions around the globe say silence reveals truth. And quantum physics says the argument is that decoherence destroys the information that you can have in a quantum computer. And you can correlate the two, and you can say that you have different languages, but you have the same insight. In one side, you have quantum algorithms and insight. And quantum algorithms do not search step by step the